So this week we are going to be dealing with work, energy, and power. So these are ideas that are sometimes separate, but they do all relate to each other. The first one we're going to talk about is work. Now, work, in the simplest sense, is a change in energy. Now, if you think back to energy in Physics 20, there's really two types that we want to be familiar with. There's potential energy, which is mgh, and then there's also kinetic energy, which we can calculate with 1/2 mv squared. So potential energy is anytime you lift something off the ground or it has stored energy in a gravitational field. Kinetic energy is the energy of movement. Now, if we change the energy of things, that's what work is. If we think about a ball on this earth, so here's a ball. If I were to take this ball and then lift it up and then hold it here, now it has potential energy. Here, the potential energy was 0, and at the top, now it has a certain amount of potential energy. To change that energy, I had to do work. Now, one other way to calculate work is a force times the distance. So to change the energy of that ball, I had to apply a force, usually the force of gravity. All right, so here I had to apply a force, which was the force of gravity, the weight of the ball over a distance, if I was moving at a constant velocity to get it to this point. In that process, so all of the work that I did went into making potential energy. So now that energy is stored as potential energy at the top. So we have some of these other calculations too, because I know force could be the force of gravity. So mg times the distance. You'll see this is very similar to the potential energy at the top. Maybe I'm moving horizontally, in which case that force causes it to accelerate, and that's over a distance. It's another way to calculate work. So work has some of these different formulas, but ultimately it is a change in energy. Power has to do with work, where power in watts is the amount of work over a certain amount of time. So something that provides more power is able to do a lot of work in a short amount of time. And that's where power kind of ties into these different ideas. So today we're going to be talking about work, about energy, and about power. Now, work can be positive or negative. So if I have a force in the same direction, so here I have a certain amount of kinetic energy. At the end, I have a greater amount of kinetic energy. Now, if my energy is going up, this is positive work. One way we can identify that is the force is in the same direction as the movement of that object. In this bottom example, I have a certain amount of kinetic energy here, but then afterwards, I have less kinetic energy. Now, this is negative work. So I'm still doing work. I'm changing the energy of that object, but afterwards, it has less energy. So energy and work is usually, like, energy is a scalar, and it is a scalar where we don't really care about direction, but we need to be careful when talking about work and the direction that the work is in, and determining whether it is positive or whether it's negative work. If I'm applying a force in the opposite direction, that's going to be negative work. If I'm applying a force in the same direction, that is going to be positive work. To summarize again, if I want to change the energy of this thing, so say, let's first talk about maybe moving this book up here. So I want to move this book, here's a book, up to the top here. In order to do that, I need to apply a force upwards on that book. to change the energy of it. So if I apply a force in this direction over this distance, I'm changing the energy of that. That is positive work. Now, if I'm moving at a constant velocity, so we think about this book moving at a constant velocity, there's the force I'm applying up. So I'm doing positive work. But there's also an equal opposite force down. That's the force of gravity. So gravity is applying a force down. Gravity would be doing negative work against the work that I'm doing. So we can have both in those situations. And it maybe makes more sense if I'm moving up and down, maybe makes a little less sense as opposed to moving side to side. So if I were to take this book and move it at a constant velocity to the right, so now the book is ending up over here. So I am applying a force this way over that distance. This is going to be positive work. But if we're moving at a constant velocity, the energy of the book is not changing, right? So here I have a certain amount of kinetic energy. At the end, I have a same amount of kinetic energy because I was moving at a constant velocity that whole time. So I have here the force of friction, which is applying a negative force over this distance. That's negative work. So this negative work and this positive work are the same when I'm moving at a constant velocity because we're not accelerating, right? So my kinetic energy before and after is the same. I haven't changed the energy of that book when I'm moving along that plane. So here's the question. Leon, super impressive, exerts a force of 520 kilonewtons to pull two train cars a distance of 2.75 meters at a constant velocity against friction. Determine the work done by Leon on the train cars. So in its simplest form, work is a change in energy, or it's equal to a force times the distance. We'll say that anything to the right is positive because that's the direction that it's moving. So if Leon applies a force of 520 kilonewtons, so that's 520 kilonewtons over a distance of 2.75 meters, then I get my calculator. So I get my calculator and I get work of 1,430 kilonewtons times meters. Which brings us to the units of work. So this would be 1,430 kilojoules. So work is measured in joules, which is the same as newtons times meters. And because newtons is the same as mass times acceleration, it's the same as kilograms times meters squared over seconds squared. These are all equivalent units when we talk about work. So joules, newtons times meters, kilograms times meters squares per second squared. So 1,430 kilojoules. If we think about the work done by friction, so constant velocity is important. So we have this applied force that we just used to calculate the positive work done. If we think about the work done by friction, so friction's in the opposite direction. So it will be a negative force. The amount of force will be the same because it's not accelerating. So the work done by friction on the train cars will be negative 1,430 joules. The net work is what we get when we add all of that together. So that train car is not changing its energy. It's moving at a constant velocity. So there's no extra kinetic energy at the end than at the start. The net work is 0 joules. I add the positive work done by Leon, again, super impressive Leon, and the negative work done by friction, and I get a net work of 0 joules. This now brings us to the concept of power. So power is the amount of work we do in a certain amount of time. Now, remember this week when you're working through these questions, all those different ways we have to calculate work. So it could be a change in energy. So what is the kinetic energy after? What is the potential energy after? That is the same as work, same as applying a force over a distance. Now we're going to identify how much power Yoda has. Not baby Yoda, but old school Yoda, real OG. We want to try to find out the amount of work that Yoda is able to do. This is from XKCD, if you're interested. So things we'll need to know. First, we need to find out how much work that Yoda actually does. There are some useful things. So from that video clip, and just kind of extrapolating, we can identify that an X-wing is 5,600 kilograms. And Dagobah, because of its size, is very similar to the gravity on Earth, 9.8 meters per second squared. We also need to know the distance that Yoda actually raises that X-wing. So going from that video clip, it's about 23 seconds. And the height we can use, or the velocity, so we know how far it moves. And so we can identify the speed of 0.39 meters per second. So we know the height that he moves that X-wing to, or the distance that he moves it to, is 8.97 meters. So we kind of have all those things. So we can calculate the height that he raised it to work. Now the reason why we want to calculate work is to calculate the power that Yoda has. Power is the work over the time that work is done for. Power has units of watts or joules per second. So it's the amount of work over the amount of time. So first let's calculate the work that Yoda does. So if we think about the work that Yoda does, it is a force over a distance. But if we think about that X-wing, here it has potential energy of 0, and then after it's raised up, it has a certain amount of potential energy. So there was a change in energy, and that change in energy was all potential. So the final potential energy is equivalent to the work done. So that X-wing is 5,600 kilograms. G is 9.8 meters per second squared, and then the is 8.97 meters. So that's how much work is done by Yoda in that clip. So 5,600 times 9.8 times 8.97 is 492 kilojoules, or times 10 to the 3 joules. Now, if you do like this work is force times distance, that's fine. The force part here is the force of gravity, so that's this part. The distance, so when we talk about MGH, that's the mg. The distance is the height, that's this part. So it's still kind of equivalent when we're talking about the calculation. Okay, the last thing then is to calculate the power, which is the work over the time it takes. So Yoda does 492 kilojoules of work, and that is over 23 seconds. Which means that is 21.4 kilowatts of power. So 21.4 kilowatts of power. What does that 20 mean? Could Yoda actually be a good source of renewable energy? If we look at just the average amount of power used in a house in 1 hour, so like maybe in peak time, so the peak time would be like around 1.7. So if you 4 kilowatts, that's roughly 12 and a half houses he could power at peak time in the winter. So Yoda could potentially power 13 houses or just under 13 houses. If we think about it in terms of horsepower, so he's 21.4 kilowatts. That would be about 16 horsepower, which is not very much, maybe enough to power a smart car. So those concepts of work, energy, power are what you're going to be using in this week's assignment. So it does say yesterday's, but ignore that. So we have chapter 5, page 163, 165, and 175. We have these questions to work on, and then this week's assignment. If you have any questions, ask them in the feed. Some things to note when you are working. We only care about the force and the direction that the object's traveling. So if I'm pulling at that angle for some of these questions, we really only want this x component because that's the distance that it's actually moving in. So if I'm dealing with nonlinear vectors, my work should be the force in that direction times the distance. We might need some trig ratios to find that force first when we are doing this week's questions.